Okay, so the last topic in interfaces that I'll cover is solid-fluid interfaces and melting point suppression. Okay, so in solid-fluid interfaces, there is a variation in chemical potential between the solid and the fluid phases. And so let's consider a case where we have a solid particle in a fluid. Oops. Okay, so in that case, we can think about the chemical potential of the fluid, of the liquid, right? So the variation of the chemical potential of the liquid would be equal to minus the molar entropy of the liquid, dt, plus the molar volume of the liquid, dp. But the pressure of the liquid is constant. So let's consider that PL is constant, not affected by the interface. It's just affected by the external pressure, which is fixed. So this would just be minus the molar entropy of the liquid dt. The chemical potential of the solid, though, is going to have contributions both from the entropy and from the molar volume of the solid and the pressure. And the pressure in the solid is going to be set by the fact that the solid is a particle. So we're assuming we have a solid particle that's in a liquid, right? So the solid particle, because it's a particle, is going to have some Laplace pressure from the interfaces we had previously discussed. And so in this case, dps minus dpl has to equal d2 gamma over r, right? That's our Laplace pressure. And we said dpl is 0, so the change in pressure of the solid due to the interface is going to be 2 gamma over r. Okay, so that means that when we look at d mu s, we can write this as minus the entropy per mole dt plus the molar volume of the solid times d2 gamma over r. Okay. So we can write the difference in the chemical potential between the solid and the liquid as SML minus SMS dt, right, plus gamma s dps, right? And we're writing this dp, and this, so this gives us delta sm dt plus gamma s, and dp we said we can write as d2 gamma over r. Now we can relate, because we're in equilibrium, right? We know that there's a relationship between delta H m, like the molar enthalpy between the phases, and delta Sm, that has to equal 0, and so we can say delta Sm has to be equal to delta Hm over T, right? So we can further write this as delta Hm over T dt plus omega s d 2 gamma over r. Okay. And then we're going to assume delta Hm is independent. independent of T. Okay. So if we do that, we get that we have that mu s minus mu L has to equal delta Hm. And so first of all, this has to equal 0, right? So we have Hm over T dt has to equal gamma s d2 gamma over r. So what we get is that delta Hm times natural log of T. So that's the melting temperature of a particle at radius r over the melting temperature of a particle at radius 0, of radius infinity, has to equal gamma minus omega s times 2 gamma over r. Or in other words, we can write this as Tm at radius r is equal to Tm at infinity, the melting temperature of the bulk phase. So the melting temperature of the particle of radius r is equal to the melting temperature of the bulk phase times exponential minus 2 gamma omega s over r delta Hm. Okay, so what does this mean? So this means that if we were to make a little graph of Tm as a function of r, right, we have the bulk melting temperature, and that applies for large radius particles. So here, let's do this in a different color. That applies at large radius particles, but then as we go to smaller and smaller particles, this gets, right, so at large radius this goes to 0, e to the 0 is 1, but as r goes smaller and smaller, the melting temperature becomes suppressed. So we get some suppression of the melting temperature. Tm is suppressed for small particles. So the small particles melt at lower temperature. So let's look at a particular case. So here let's consider platinum. The surface energy is 4.2 newtons per meter, or Newton meters. The molar volume is 9.09 centimeters cubed per mole, and the molar enthalpy is 20 kilojoules per mole. And if we put that in, and we know that the melting temperature for platinum is 2041 K, right? So we could figure out where, at what radius does this become significant. So Tm is suppressed when r is less than 2 gamma omega over delta Hm, and that ends up being around 30 nanometers. So this point here would be around 30 nanometers for platinum. So below 30 nanometers, we'll see a significant effect. So this is a nanoscale effect, but it's a real effect. The melting temperature will be significantly changed if we go below 30 nanometers.